Let me explain you quantum cryptography in several minutes. And I promise you to not share any classified governmental secrets. Any piece of information in our electronic devices is represented by zeros and ones. That so-called encoding is the way to represent the information. It's not about hiding information, which is encryption. It's more like how do we represent our spoken language by spelling in letters. So if I want to send a message, for example, Mom, I eat healthy food every day. It has to be encoded in zeros and ones. And only in this shape it can be transferred, since we are using electronic devices, not radio. So the message has to be encoded and probably additionally encrypted to do not let people steal it. The problem is, the message can be stolen, though it stays encrypted, but in the future it probably can be decrypted. Okay, it's not that important if I share hi to my mom, but if it's some important secret information, it already changes the situation. Here is even a strategy so-called harvest now, decrypt later. Many of security protocols were already broken, and we don't want to have a new protocol which is broken. Probably we can somehow protect that on the physical level to make it somehow unstealable. And that's what quantum cryptography is about. So those zeros and ones are streamed through electronic wires or through optical fibers. That's a new technology, I like it, and it's exactly what's used in the quantum cryptography approaches. In case of electron, we encode 0 as low voltage and 1 as high voltage. For the optical case, we can encode it in low intensity and high intensity of light, or either in two different polarizations of light, vertical and horizontal, or for example left and right curly. And here's the trick: the high voltage and high intensity of light has a lot of electrons, either photons, and from those many electrons and photons we can steal a little portion. A regular laser pointer emits an unimaginable amount of photons each second, and our technology allows us to steal a tiny fraction, and we can detect on the level of single or couples of photons with unimaginably high precision. So we don't need to steal much. The question appears, usually the communication line consists of thousands of kilometers, and we cannot ensure no one is listening to this communication line. We cannot place soldier each, 50 meters. Moreover, if we do, we don't trust each of them, probably one of them will steal it eventually. So we need something to protect on the hardware level, to make this communication line unlistenable and the message unstealable. The question is how to do it. And I gave you a tip: number of photons. So we are ending up with quite simple solution. If there are millions of photons in each the pulse, we can probably drop the number to 1. If there is only 1 photon, we cannot steal it. Or if it's stolen, we will note it. That's the simplest idea. There are more deep ideas using entangled photons, blah, 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 but that's the core. We have to drop number of photons from millions to 1. And it brings us already to quite interesting problem. To make this, we need 2 things. We need a way to detect the single photon on the high rate, so many photons per second. And secondly, we have to somehow emit those photons. As for detection, there is already quite good established technology, so-called superconducting nanowire single photon detectors. But what's about emission? With the emission is a bit more complicated, because we need photons with special properties, as a color, as amount per second, and it has to be a single photon. And most of the light sources you can imagine cannot give you single photon emission. As for example, lamp. If you look into the light beam, how the photons are distributed within this beam, you'll see they are not evenly distributed. There are some bunches. And if you attenuate it somehow, if you place some light filter which will absorb, 99.999% of the light, you will not have photon, nothing, photon, nothing, photon, as we would like to have. You will have 5 photons, nothing. 3 photons, again nothing. For laser, it works surprisingly samely. So we have to construct light source of some special properties. Quantum light source. Fortunately, such quantum light source exists, and I am showing you an imaginable amount of them. They are atoms. Not each atom can emit you light of the desired wavelengths. So it can only emit the wavelengths it can emit. But for telecommunication, we need some special wavelengths. 1.55 micrometer, it's infrared light. And as far as I know, there are not too much atoms which can do it. Moreover, they cannot do it with proper amount of photons per second. My God, how stupidly I told intensity. Amount of photons per second. Atoms can emit single photons. Why does it work so? If atom has 2 levels, an electron somehow jumps from the ground state to the excited state, it's only 1 electron, and when it jumps back, it emits only 1 photon. So it's a single photon light emitter. There are many problems with a single atom as single photon light source, because it's problematic to keep it, it's problematic to pump it, and moreover, it does not emit much photons. Main problem of a single atom, it does not emit light effectively. Simplifying, wavelengths we want to emit is of, let's say, 700 nanometers or even 1.5 micron. It's huge, but size of atom is somehow sub-nanometer. So it's 1,000 times smaller than the wavelengths it emits. And the good light source must be roughly of this size. And there is a solution, several solutions. First of all, to improve that, we can use Purcell Effect. I did a video about that. There is an effect which helps to improve intensity of the light emission from the single photon light sources. And it's that fancy, you can consider it a magic outside of Hogwarts, my friends. The core of the effect is mind-blowing. One mirror reflects light. If you place second mirror consequently, the system is getting totally transparent, even though each of the mirrors reflects light well. And there is a video explaining how does it work. But for us it's important that system of those 2 mirrors is forming a standing wave, and if we place light source in the antinode of the standing wave, it amplifies emission kinda like a nano-antenna. But for some reason we don't say word nano-antenna. Please subscribe me or not subscribe. It's your life, so please make a wise decision. Another solution would be to use artificial atom. Nowadays we have not only artificial intelligence but also artificial atoms. What it is I explained in another video. For you, simply it looks like this. Its optical properties are exceeding optical properties of the real atoms. For instance, it has tunability, so we can choose the certain wavelengths it will emit the light. But samely as the real atoms, it has a problem with directionality, so it emits light in all the possible directions, samely as light bulb. But we need the light to be collected in the optical fiber so that we can use it in some telecommunications, in any applications actually. And this Purcell effect is also used for this. We need a system of 2 mirrors, and then directionality changes from all the directions to the chosen by those 2 mirrors. If there are many electrons or many photons, they can be stolen and your communication line can be listened. But if we reduce amount of information carrier to single, then you can make quantum cryptography telecommunication line. In the real life, we make a 3-dimensional system of Bragg mirrors. It looks very fancy, which are actually 3-dimensional mirrors. Bragg mirrors, I did a video Bragg law, please watch it. So in the fact it looks very fancy this way, but the physics is roughly as I explained right now. If this video gets enough views, I will explain what's going on in this picture step by step in one of the following videos. Please subscribe me to not miss. Please like this video, subscribe me or not subscribe. Choose your destiny by yourself. Be a driver of your life. And write your comment. It's really helpful for my growing channel. Thank you for watching and see you in the next videos.